Hello, everybody. My name is Arman Khalatyan, and I'm a researcher at Leibniz-Institut for Astrophysics, Potsdam, Germany. And I would like to thank to Sandro Bonazzolo for inviting me into this conference. And it is really great pleasure to be here because we are really fans of oVirt and we are powerful users of that. And I would like to share our use case at AIP and how we are going to expand our deployment. And as you can see from title is some kind of about microservices towards to reproducible science. I will share here some ideas how we are going to proceed that further. Before going further, I would like to present our institute. Formerly, our institute was Berliner Sternwarte, located in Berlin. Once Berlin became really noisy due to the cars and very bright due to the evolution, it was moved outside from Berlin to Potsdam, next to the Potsdam in Park Babelsberg. And several times our institute changed its name. Finally, in 2011, we renamed it Leibniz-Institut für Astrophysik Potsdam, which is emphasizes that we are a member of the Leibniz-Gemeinschaft. And in this point, I would like to point out that already we see here that several dates are tracking the name evolution of AIP. And a similar thing one should be able to track. For example, if you have a data set and you change the version your data sets, you need to be able to reproduce all this history and how it was rename it or redeploy the data sets. Our institute has also really rich history, but we have also two sightseeing places. If you visit Potsdam, just go over there. One of them is Great Refractor, is another one is so-called Einstein Tower, which is considered as a milestone in architecture. But even if you cannot visit us due to the whatever reasons, you can go to the virtual reality tours at the RIPDA, which is running on oVirt. So our research areas are covering from solar neighborhood up to the extragalactic astrophysics, and we are not only doing observations or participating in international projects, we are also building parts of the telescopes, and we have also construction workshops and labs for instrumentation, which is pretty impressive. And besides that, without this modern infrastructure or in order to do modern astrophysics without supercomputing and eScience infrastructure, you cannot do modern astrophysics. So we are hosting in-house almost 2 petabyte data storage, and we have several clusters. And not only bad data sets are stored there, we're also serving databases over the web interfaces which are developed in-house. Myself, I'm a cosmologist, and my main research area is galaxy formation in gas dynamic numerical simulations and connecting that into the observations. The idea is that you have some model, and based on that model, you put your code into the supercomputer running several months on many, many thousand cores, and you try to understand how the universe formed and how inside this universe single galaxy formed there. And of course, without supercomputing, without parallel codes, and without different tools like visualization, special visualization tools, or big data juggling, this research wouldn't be possible. So for that, one need to have some kind of infrastructure. In we are using open source tools whenever it's possible. As you can see in this slide, we are our main operating systems are Debian or CentOS, and of course oVirt, we choose that as a virtualization tool. The oVirt at AIP, we started to use that around maybe oVirt version 3.5. It was since 2016, but probably the most of the fully into the fully integration into our infrastructure. It was already starting from 3.6. From this is actual screenshot of our infrastructure and of our clusters, and you can see that we are hosting almost 80 virtual machines. Some of them are market high HPC virtual machines. Mostly the virtual machines are used for hosting web pages and data reduction for testing purposes. And I would like to mention here the oVirt has very supportive community, and we are really happy with that. And it was helping us several times to overcome with the problems. From this screenshot, you can see that our infrastructure is not so loaded and one would think, but we have several HPC virtual machines which are used for data reduction, and sometimes when the data is arriving from satellites or from telescopes, then our workload is going up to the 100% on some virtual machines, and this is very imbalanced situation in some cases. And I would like to mention that this why to use virtual machines into inside these pipelines, data pipelines, because of sometimes the data are arriving over the 10 or 20 years, but your computers are becoming old and you cannot find even their spare parts to repair, and better to have them encapsulated inside a virtual machine so you can move them from host to host easily, independent. So you are becoming independent on hardware. Also, if you have some kind of different versions of pipelines, you might snapshot them and keep as a snapshot of the virtual machine. And usually, what are you expecting from such an environment as a scientific community? As astrophysicists, if you ask them, what are you expecting from the new computer or from the new environment, if you propose them to use that, they would say, in the first place, we would like to have the fastest hardware inside there, like GPUs or SSDs, or it should be high available always. But of course, one of the important part of the demands in some projects that it should be like very strongly connected into the parallel file systems where you can analyze terabytes data in reasonable time. Of course, it would be great to have some reuse or reshare unused resources to be more or less green, and of course some projects that require temporal some kind of services cloned and then on demand provided them. Buying hardware is not enough, so that's mean one need to provide for the users some kind of software infrastructure where they would like to have all data, their source code, or even cluster access, everything in one place. And this complexity needs to be obscured from the users, and recently we get even many requests on how one can publish on demo notebooks, Python notebooks to collaborators and show what they achieve. I would like to show here some example of such a notebook where we were running this notebook on about 500 core job, and we are juggling here about 250 million star data almost on real time using Dask library. And such examples to share with collaborators is very valuable, because on a real-time analysis you might see some new data feature which is crucial in science, and you can find something new. And one of the possibility to hide this all complex infrastructure, hardware infrastructure, beyond the software, we found the very useful the CoCalc project, which is a web-based cloud computing and course management platform. It's a part of the SAGE project, and mostly from this project we are using LaTeX, document editing, and the Jupyter notebooks. And for simplicity, one can imagine this whole infrastructure, what we build it up to now on top of the oVirt, looks like this. Is like a puzzle, very complex puzzle with every small piece plays where every small piece plays a big role. Assuming you have a user with his own data and algorithms, he is going over the Colab interface and accessing the data sets. They have own Python or interactive plots, so they can now in current setup select or choose own environment given version of libraries. As you know, most of the libraries in the Python, they are conflicting or versioning problems always striking us, and to overcome that we have different environments for every project, and they can access to those environments over this Colab web interface. A beautiful thing of that you can put this all software into the virtual machine, and this virtual machine is running some Docker container. So we have Dockerized version of the CoCalc project and our instance called Colab IPD. And this also has a direct connection to our clusters, and over the 10 gig, we have connection to the Lustre file system. Of course, this each box one can assume as a small part of the project, and we can separate these all layers in that way that one can think about, well, if we separate these each pieces, how we can find the best solution of each this puzzle part. And before going there, one of those requirements were if we virtualize this all stuff or Dockerize all this stuff, do we lose some kind of performance there? And here I'm showing one storage benchmark. One of the big questions were how we bring this terabytes data into the project. And in the left side, I'm demonstrating how quick one can read the dataset based lying on residing on a Glasser file system or some storage, ZFS storage, which is like ISO exported storage. I don't want to go into details. Nice thing from this benchmark is that if you use the checksum or even DD on a bare metal, and if you use inside the virtual machine, then the performance of reading datasets from Lustre file system or from ZFS file system is reasonable fast or quick for our usage. So this virtualization part is not striking strong. And here we can see the Glasser file system is always a little bit slower than other storage things, but of course one need to think about do you need to have very strong availability of your data sets, or you want to have a performance. In this case, we choose the Lustre file system for that data sets which are just simply raw data, and for ZFS file system with snapshotting, we are choosing for those data sets where we have user data which is snapshotted and kept safe. So another point was in our oVirt, we were really happy to have this result because of requirement on GPU support of this environment. allows us to run machine learning algorithms inside this project. And this hosted dev pass-through method allowing us to provide GPU to the virtual machine or even Docker container, which is running inside the virtual machine with its full performance. And in this left side of the benchmark, you can see this is virtual machine, which is running inside the Docker container, a virtual machine running inside the oVirt and Docker container, which is running inside this virtual machine. The both are providing us very reasonable results for benchmarking. And as a comparison, I'm just showing here also some kind of overclocked gamer desktop machine with 2080 Ti to see the quality of the T4 GPU, which is really low power GPU, just suited for machine learning algorithms. And once we have these nice results, now the question is how we can apply this through all these puzzles, how we can bring them all of them together, and we can mark those these services, so-called, or this part which is software, or which is a little bit set of the group of the software. We can call them as a microservices and encapsulate them inside the, let's say, some Docker containers, and we can provide them as a group or as a separate service into the users. And first application, we were thinking just using this Colab project, and that every project might become as a one microservice. So every project might become as a one Docker container or one pod. If we are talking about OKD or OpenShift jargon, then every this project might become as a pod. And if we go further for reproducibility of the science, one can think about that some kind of data analysis pipelines with versioning, and the Git and Git integration might help us, or with continuous integration with GitLab, we might achieve this reproducibility of the science. So every time when one change the pipeline, you can roll back and forth, make branches. And publishing interactive papers, like providing like a binder service for own papers would be possible if one used these microservices. Or even a very beautiful example, this DistillPub provided by Google, this way how you publish your paper. I believe in the future most of the real science papers, they should become, or they should be published like this DistillPub way, like Google does. If we go more steps that maybe this distributed development will be would be possible with these microservices. And in some cases, if you have some delaying environment, then you might save power or resources. But we had also some concerns. If one look in these environments, then the complexity might arise, and also you need to think really carefully about your design, how you start to deal with your pipelines, and testing and debugging might be a problem. And also some of the tests that were showing this inter-service call latency might strike for some projects. For example, you cannot run MPI parallel jobs over there, but if you massively scale up with some libraries, it might help a lot. So what we did, actually, we choose OKD for our ideas testing such a test bed. We install it minimum environment, like one infrastructure node, one master node, and one worker node, and everything is running on oVirt. And this also integrated. The OKD installation is also integrated within the oVirt using the oVirt storage as a persistent storage for OKD. So it was extremely hard to deploy this whole environment. And over the almost 10 unfixed bugs in that time, we needed to run and look around and read GitHub and read Ansible source codes to understand why it's failing on one node or whatever. But finally, we succeeded. And once you have this very powerful environment, what you can do with that? First of all, we deployed our collab environment. And this collab environment is constructed in that way that every project is one pod spawned on a OKD, and each users which are logged in into the web interface, they might be landing on a given project if they have access to that project, and this project might have different CPU quota or different disk space quota or even memory quota. Here is a environment of the screenshot of our deployment. It looks like pretty impressive that every time when a user is logging in and he has some project currently running, he's starting in the background, the OKD is spawning the project as a pod, you can see here. And for example, in this case, the users were accessing 3 different projects, and all of them, they were spawned simultaneously. Another interesting application of this environment, we found that one can deploy own notebooks as a little small apps. And deployment steps are following. You have a source code as a Docker container on a GitLab, and in a Git you enable your continuous integration, which does 2 deployments on OKD, on a Kubernetes, and then you can look if your staging deployment is okay. Then you can trigger manually the production deployment, and he will build and recompile this container and impose as a service, as an application inside the OKD. And if we look in such an example here, I just deployed a simple streamlit application, which is pretty new and very awesome project. We tried to play around with this application, how we can publish some results with interactivity on that. And you see here the bokeh plot, or selecting number of stars from the given database. Actually in the background, when you pull this scroller, it downloads from the remote database the part of the stars, and you have here some kind of explanatory plots for your results. Another deployment example here is shown using the technology like source to image from OKD. If you are not familiar with that, source to image is a toolkit and workflow for building reproducible container images from source code. That's mean if you are hosting somewhere on a Git project, some Jupyter notebook, then you might be able to deploy that as a standalone app on OKD. And this is very easy using these image streams. And in this example, if you follow, then only using 2 or 3 commands, you are able to deploy as an independent application, which is hosted on GitHub. And of course, one can also build up own apps based on that already build it up with his own variables or parameters. Let's say if you have a Jupyter notebook, you restrict the access to that notebook using some password, and you can also even redirect all these routes using by one command all insecure HTTP requests directly to the HTTPS, so your application is becoming secure. In the end, if you look here in the roots, so you get some kind of project application name, then project name, as a URL in the end is your Okade instance name. This is very useful for the future reproducibility of the pipelines or for deploying the reproducible software with different versions or branches. And I think this is very powerful tool will become in a future one of the Matadori utilities in our environment. So going to the conclusion, in our experience, we can proudly say that oVirt is well suited for academic workloads, and even more, one can also use that for high performance computing and big data analysis. And as we shown in this presentation, some reproducible pipelines one can organize using two complex projects together, Okade and oVirt. If you marrying them together, then you can achieve very, very strong results. And I would like to mention here in the end some kind of, it's nice to have some kind of long-term support for oVirt. Unfortunately, it's all these technologies are developing very rapidly, and in some point you're overwhelmed by technical parts instead of this fancy scientific part. And would be nice to have very good integration with InfiniBand infrastructures, because in our case, all our data flows are going over the 10 gig interfaces and as a routers, which are bringing data sets from the InfiniBand. Maybe there are some kind of ways to do that, but it's nice to have in the future better integration with the InfiniBand network. And one of the biggest missing puzzle is high performance storage in this whole environment. And in our tests, we have seen that GlassFS is still slow for our purposes, but it's pretty nice project, and I wish that in some point GlassFS will become powerful enough to hold concurrency with raster file systems. And thank you for your attention. And if you have some other questions, let me know. And I have a very short announcement that in the end of this presentation, I have also supplementary 2 slides, which are just showing the example between Monolith and some microservice-based infrastructure or application based on an example of our VR-point IPDE web page. And I don't want to go into these details, but if you're interested in, you can just have a look at the supplementary material.